So it is definitely difficult to see what I write in a broadcast, even with a 720p, which is the best I can currently broadcast without freezing the computer, right? So I'm going to have two things here. Steps are going to be in purple and evidence is going to be in red. Okay? So you probably should want to do something similar to what you do. But let's talk about origin. Now, remember, everything we've been talking about so far is evolution, how life changes over time. But this is different. This is how life started, and that's a different topic. So even if evolution was proven beyond a reasonable doubt, because you do that in biology or in science altogether, but we have a lot of vast evidence. We had a whole class about that. The evidence for evolution, which is available on the left side of things. But what about this? This is different. This is about starting, origins. And there's a lot of theories hypotheses, sorry. Don't use the word theories here. Because if it's theory, it means it's based on a lot of evidence. Now, I'm going to put a lot of evidence on the board. And some of them in green will be more like logic than evidence. Alright? More like logic than evidence. But one of the first things I want to make sure it's clear to you guys is that the biologist's vision for the origin of life is based on principles of physics, chemistry, right, and the laws of the universe operates on. It is not a random process. Because people think and say, how could random processes create life? Well, first of all, it's not random. Another common criticism people use is, if this could have happened, and it did happen, why can't we make it happen again? Right? Well, nobody said we can't. We could absolutely make this happen again, and we could dedicate thousands of dollars to put this in a lab somewhere, and there's probably someone doing it, trying to replicate this thing. But this is actually a process that took 1 billion years to take place. And for 1 billion years, 1 second at a time, life had attempts at this. So it just might take a very long time. Because here's the thing about random things creating, by the way, again, it's not random. But if they were random, here's the thing about random things creating order. If there's a small chance of something happening, even if it's astronomically small, if you have an astronomical large number of opportunities, such as a universe with 10 billion galaxies and 10 billion stars, and I don't even know how many stars in each galaxy, but it's billions of galaxies in each galaxy, and then billions of galaxies, right? And then each of those stars may have planets, and then all of those potential, and that's just the observable universe. We don't know what's beyond the observable universe, and all of that vastness of space. There was just so much time and opportunity that somewhere, if there was a chance, it would have happened. And that's the thing about it. What I'm going to describe now is it's a probable process. It's a process that's actually potentially possible. And since it was potentially possible, even a astronomically small chance. Now here's the other thing. That's assuming randomness. What I'm going to describe right now is not a random process. It's a process based on physical laws, and therefore not random at all. The Think About It videos, which are on the board right now, those things, there's some of them that actually break this down in detail for those of you who are interested. And I have a lecture series where I break this down in detail for the ones which are interested, right? But this, I'm going to go over a little flash review of the steps you would need. Now, life, as it exists today, this is the other thing, is very complex. So what people expect when they make life is to make a prokaryotic cell at least, right? But for that you need to have ribosomes, a DNA machinery, a replication process, a protein synthesis mechanism, right? You have to have cell division organized. All of that is very complex. Our end goal, on the other hand, here, is not complex prokaryotic life. It's something very simple, right? Something much simpler than that. We need just something like this. This is our end goal. We need a protective layer surrounding a self-replicating molecule. And if you get this far, the rest is evolution. And that's actually something that, if those of you who are interested, fascinated by this awesome biology here, just spend some time and watch these videos on Think About It. Because it will really do a better job than we could possibly do here and explain all the evidence behind it. Okay? But all we need is a protective layer surrounding a self-replicating molecule. A self-contained homeostatic environment that has the goal of making copies of itself. And then from that, you have evolution. So let's see if we can get there, in a couple classes. So the first step you would need, before you can even talk about that. Now we're talking about a self-replicating molecule. What type of molecule is that probably? In the other chapter, so what talking molecule I'm probably talking about? Come on people, you're supposed to read the chapter. If you don't come ready for this, then it becomes less of a discussion and more of a lecture, and it's not a start. Yes? What molecules are I probably talking about here? Sorry? No. A molecule. A molecule.
An amino acid.
Amino acid? Well, that's not just one amino acid. That's a self-replicating large molecule. What am I talking about? Yes?
DNA.
Either a nucleic acid or probably RNA. Right? That's something else we're going to talk about probably next class. It's something called the RNA hypothesis, which we think RNA was probably the first one. Okay, but we're talking about RNA though. But RNA is built off nucleotides. And nucleotides are built off phosphates, right? 5 carbon sugars, which are organic molecules, right? The pentose that's in there. And then a nitrogenous base, which is again an organic molecule, right? Today, nitrogenous bases and pentose sugars are made by producers, right? You can make them too, because you have biological process for that, but it starts with the producers. You need like something like an algae or a plant to do it, or a cyanobacteria to do it. So there aren't any biological processes going around today that's making nitrogenous bases. There are biological molecules. So the dilemma becomes, how do you make a biological molecule before biology exists? Seems counterintuitive. Is that possible? That's a very important point. So we need to make a macromolecule. And then what about this thing, this protective layer? What are we even talking about? Dig deep in biology on this. What are we talking about? What is this protective layer here? A cell membrane. What is it made of? Phospholipids. And phosphate is a naturally occurring chemical. But what about these lipids? They're a combination of glycerol and triglycerides, which are very self-repeating units of molecules, again, built by life. Again, so how do you build? At the very least, you need these things, right? So that means our first requirement is thinking about macromolecules. Before we even have a cell, we have to make these things a cell of beta. So we can't have a Lego building without Lego blocks. But the things that the Lego blocks themselves, now I'm talking about amino acids, nucleotides, fats, right? Those simple building blocks of the larger molecules that we're interested in also have to be built. They are anabolized by life today, right? So then before we can talk about building big molecules, we have to talk about building small molecules, or having them around for somehow, right? So before we can even talk about the origin of life, we have to talk about the origin of macromolecules. And before we can talk about the origin of macromolecules, we have to talk about the origin of organic molecules, simple, smaller ones, right? Things like amino acids and simple fats and nucleotides. But before we can talk about the origin of that, we have to talk about the conditions that life could have in order to have those molecules create themselves. And that takes us back to the beginning in the history of the universe and all that stuff. But accelerating to the very early stages of where life could have formed, we're talking about an early Earth. And there is a hypothesis, or two, that describe this. So the first thing, I'm skipping all the other stuff. I'm skipping the Big Bang, I'm skipping the formation of the Earth, and all this other stuff. But it's not important. It's on my lecture. When I talk about formation of the Earth, for example, things which are important, okay? Could life have formed prior to the impact with the moon? Well, with the thing that caused the moon. Because actually, the moon is not the thing that impacted us early then. Something hit us and kept going, but it tore a chunk of the Earth. And then from that, the chunk, the moon consolidated to form. That caused the Earth to go back to molten. And so if there was any life before then, it was probably eradicated. So we can't even talk about any formation of life before 4.3 billion years in that giant impact hypothesis, which has been corroborated by a lot of different things in science. And then, what about the formation of our atmosphere? Where do you think our atmosphere came from? Volcanoes. But volcanoes spill things like methane and carbon dioxide and sulfuric acids and all kinds of different noxious gases, which are different from the nitrogen-rich atmosphere, ammonia, different from the nitrogen-rich atmosphere and oxygen-rich atmosphere that we have today. So how do we get to that? All right? Something else we have to talk about. We talk about origin and history of life. Where is this atmosphere coming from? Where is the nitrogen coming from? Right? Where is the thing coming from? All right? We'll talk about that. All right? So, but it's important to understand that by now, before we even start, we're talking about an Earth that's become cool enough that the crust, I mean, that now you have continental shelves already established themselves. You have the plate tectonics already doing what they're doing, and you already have shallow oceans coming from the rain that comes from the vapor that's coming from the volcanoes. Earth's gravity is strong enough to create this layer of gases over our atmosphere, right? Coming from the volcanoes that are spilling these gases, and the water vapor and everything rains down and called this shallow ocean. So this idea of a shallow ocean that would have a bunch of these volcanic chemicals in them. Anybody remember the name of the hypothesis? Yes. Primordial soup. Alright? So primordial soup. So the idea is primordial soup. Anybody remember the name of the scientist behind this one? It's either Haldane or the other one. I don't know which one it is. But what I don't want to say Haldane and be wrong. But it's a scientist that did a research on this. But you didn't have this. It was Haldane? Okay. Putting that in yellow. So Haldane provided evidence for this, and his idea came from, not from some random, like okay, there was a shallow ocean full of the basic compounds that come from volcanoes. Alright, now, this primordial soup hypothesis does not come from nothing. He has some evidence to support it. Evidence comes from rocks, from geology. Alright, from geology. Because we know today what volcanoes put out, right? We know also from old rocks dated with the kind of dating that we talked about in the Evidence of Evolution, the uranium lead series dating, that very, very, very old rocks, all right, show evidence on them of just that kind of chemistry, right? So geological evidence of the chemistry of the early Earth support that we had that. Also, the rocks have, early rocks, as far as 3 billion years, show evidence of ocean erosion. Right? How do we know? Because we can see rocks today getting eroded by the ocean, and we can see how that looks like. Then we find a rock buried underneath a very deep layer or exposed by something like the Grand Canyon, although the Grand Canyon only has more recent rocks exposed. Right? But if you look deeper in other places, like Australia, that has cratons that are 4 billion years old exposed, right? Then you can actually see old rocks, but then there it is. Evidence of ocean erosion. That's because of those shallow oceans that existed. Alright, so remember that what I'm talking about here is evidence of early erosion and evidence of the chemicals, of volcanic-like chemicals trapped inside these rocks, the old rocks. Right? So in this, it goes rock dating, it goes looking at erosion patterns, and looking at the chemical composition of the rocks. So there's a lot of things that branch out of that, right? So you have dating with the uranium lead series to see which rocks are old. Then you have erosion patterns that you're looking at to prove that the rocks are indeed shallow ocean eroded. And then you even have things like, what else did I say? Chemical composition of the rock. And all right, how can I help you?
Yes.
All right, just leave it in my desk. Oh, we need to sign it? I think someone in your capacity that's actually teachers to sign something should call around with a pen. Just saying. You have one? Because we don't always carry pens with us. You will make every teacher you're going to visit after me very happy if you carry a pen with you. Grab one and take it along with you as you go. All right? All right. Okay, alongside this idea of the primordial soup, let's talk about the atmosphere of the Earth. Now, there's a hypothesis that says the atmosphere of the Earth was reducing. Okay? So we have what's called a reducing atmosphere. Why is this important? And who was the scientist there? Another guy over here. That's important. And again, this comes from rock chemistry. Operating. Alright? So if you look at rock chemistry, you're going to find something very interesting in it. Primarily, the lack of oxygen in old rocks. Now, the lack of oxygen gas is very important because presence of oxygen gas would make everything we're going to talk about now very unlikely. Because oxygen is a bitch. Okay? It loves to suck up electrons. And that gets in the middle of a lot of chemical reactions that we have to talk about now. Because that oxygen trying to grab these electrons, oxidizing things basically, right, actually would cause problems for the formation of the early molecules that we need to. Now, recent experiments have shown that even in the presence of oxygen, the chemistry would have worked, but it's less likely. And so, it's actually nice that the rocks show that there was no oxygen around. Alright, so then we have a reducing atmosphere full of volcanic gases, right? Lack of oxygen, and what do you have instead? You have things like methane, CH4, NH3, which is NH4, which is ammonia, right? You have things like carbon dioxide, you have things like sulfuric acid and phosphates. All of this is coming from these volcanoes. Phosphoric acid and sulfuric acid, right? Sulfuric acid is actually H2SO4, right? H2SO4. And you have phosphate for sulfuric acid. I think it's something PO3 or something like that. I forgot what the number is. But the point is you have these chemicals which are coming from the volcanoes. Now notice, what we need to make the current atmosphere is there. There's the nitrogen to make the nitrogen-rich atmosphere. There's the oxygen to make the oxygen-rich atmosphere, right? Oh, we have water vapor too, of course, coming from the volcanoes. Right? This is just volcanic chemistry. The stuff that comes today, right? Even today, volcanoes spill out the same thing. But remember that the rocks show evidence of this kind of composition in them. That the gases that were in the atmosphere were like that. So you can see sulfuric acid, phosphoric acid erosion patterns in the rock. Right? So anyways, this is evidence to support the fact of an early Earth with a shallow ocean, with an atmosphere full of gases which come from volcanoes, right? A shallow ocean where some of these gases would also be the liquids that come from those massive volcanic clouds, raining down, forming a shallow ocean, primarily water, but with things like those things dissolved in it, right? Then come the next big step. This is a huge step now. And this is a big question mark step. Because can we prove that this is possible? Because now what we need for this next step is we need abiotic synthesis. Abiotic synthesis of organic monomers. And what do we mean by organic monomers? I mean things like sugars, simple sugars, right? Like the 5 carbon sugars we need to make nucleotides, right? I mean fat units, right? Things like the things I need for the lipids, simple lipids, right? I need things like amino acids, right? So these basic things I can't really do. I need nucleotides, right? Because without this, I can't build the molecules of life, right? And that's the problem, is that the molecules that I have right now swimming around, it's all there. I can make it out of there. The amino group is right there, NH3. The carboxyl group is this combined with some other oxidants, right? It's all there. The things I need to make the chemistry of life is there, but it's all jumbled up. Can I make these molecules without life? Life today can grab phosphates and sulfates and water and carbon dioxide, right? That's what producers do. They get these basic chemicals and actually build these things out of them. They have the chemistry to do it. They use the sunlight as a source, right? But could that happen without life, right? So we have two leading pieces of evidence or ideas to do that. So this is 100%, right? First one of them is an idea of, what did I say? So the key terms, that's, I want to say fun. Something else. Like that, the idea that these things were seeded in our planets by comets, right? So the first evidence, I forgot the name of the hypothesis right now, but I'm going to put things, comets and meteors.
The Murchison meteorite?
Not yet, that's something else. Well, no, that's actually, yeah, I can put that in there. Murchison meteorite. But I want to know the name of the theory. It's not, gosh. All right. There's two. One of them is the idea that advanced beings are actually putting life on Earth, and the other idea is that actually just in the universe there might have been these organic molecules, and it fell. Why? Now this sounds like weird. I owe you this thing. I need this thing here. It's in my lecture guide. If you have a tablet or something, if you go to the folder for Origin History of Life, and go to the lecture guide, it's going to be in there. You can help out. The second idea is actually Earth formation of those things. And for that, we have the Miller-Urey experiment. Now, do I have to show a video of the Miller-Urey experiment because as primarily you did not do your homework and you had no idea what I'm talking about? Or if I tell you what it is and talk about it, you have a vision in your head of what it's like? Who wants to see a video about it? See? Now, a bit of a class waste, though. Okay? We don't need time. We don't have time for that. We only have 10 minutes. Please watch or read about the Miller-Urey experiment. This is just a review here. Now, when I talk about this is, what do we have there? What are the basic things we have? I'll go back to this in a second. What are the basic things we have in there? We have a container full of liquid that's being heated to make the liquid evaporate and turn into the gas stage. That's simulating the effect of the sunlight hitting it and causing evaporation, right? Then we have this container of gases, right? And in that gas container, you have sparks, which are representing the lightning, right? Providing an energy source, right? And then that gas is full of these things. The reducing atmosphere gases, right? Then falling from that, there's a collection tube, right? That goes back into the same pool that evaporates again. But in between, there's a little gauge that you can open up to collect samples before it falls into the thing again if you want to. They don't actually collect samples all the time. They just let it run for a while, and then when they're ready, they just collect samples to see if there's anything forming in there, right? You can totally do this experiment. It's actually a classic experiment that in college we don't even do it, but I never did it. But you can totally do this experiment, right? It's not too hard to set it up, right? There's some things which are a bit dangerous to have it around in the lab, but it's not that bad. It's just sulfuric acid and phosphoric acid. It's fine. It's all you have anyway. But ammonia, the things that you're going to have anyway, you put it all in there, and the sparks happening, whatever. When you do that, what happens? It forms amino acids, lipids, nucleotides, things like that, without any help. There's no life doing it. It's just lightning strikes. Now, there are criticisms to this. They say, well, you're forming it, sure, but the same process that is forming it, the next time around, the lightning can destroy it. What is in the early Earth trapping that, protecting it, like you are, in a little collection vial? Right? You could have some of it rain down and be in the water and got diluted in the water and then go inside of underneath a rock somewhere. Right? It doesn't have to stay in the air after it formed. It could rain down. Right? But remember that they don't just start it and immediately collect it. They let it run for a while, right? And so it's not as if they're not letting it go through it again and again. It's over time that it collects. It's over time that it collects. Are you with me on what I'm saying? Over time that it collects. If I have time, I'll show you a video about this in a second. Okay? Alright? Nobody looked up that lecture guide for me? Go to lecture. My tablets would work. Panspermia, thank you. Not theories, hypothesis. Alright? Now, panspermia is more the idea that there's something out there purposely going around. Have you guys seen that movie Alien, but that prequel to it that came out 3 years ago? There's a movie about Alien, the actual one that's scary. And there's a prequel to it that came out like 3 years ago. That in the beginning of the movie, it showed that life on Earth started like that, right? Supposedly. But there's also the idea that it's just comments. Okay, because here's the thing about this. The Murchison meteorite is a meteorite that fell from outer space. And of course, it's a meteorite, right? So it fell from outer space. It comes like, I don't have to say this, it's kind of like redundant. So the meteorite has amino acids in it, right? Now the interesting thing is that amino acids are produced by life here on Earth, right? But you always have it in it, which shows that, and in fact, by the way, let me preface what I just said by I said amino acids are produced by life on Earth. Not necessarily. There are free occurring amino acids, but primarily amino acids are living biological molecules, right? A biological molecule in the sense is associated with life. It's not living, right? But the molecule of amino acid was inside of meteorite. So what does that mean? Shit, is life in outer space? Not really. What we're saying here is that amino acids can form without life. They form in the outer space without life, right? Natural processes in the clouds of outer space can form amino acids. So there you go. You can have amino acids without life in outer space. You can have amino acids without life in a container. So is it or is it not possible to have amino acids without life?
Yes. It's possible.
Possible. And remember, all you need is a possibility. Once it's possible, there's no longer a random process, right? It's based on physical rules. So whether these chemicals came from outer space or whether they were produced on the early Earth, we have a primordial soup that may have included simple organic monomers. Now the next big arrow is also a question mark. Because we need to know, how can we go from that to organic macromolecules? Such as nucleic acids, lipids, carbs, and proteins. Today, if I want to make some carbs, there's enzymes in your body that make it. Make glycogen, it's a carb. We make it out of simple sugars. Plants can make starch out of simple sugars, right? And they can also make cellulose out of simple sugars. There's some fungus can make chitin out of simple sugars. Lipids, we can make lots of fat, unfortunately, right? And plants can also make fat. They put it in oils usually, but they make fat. Nucleic acids, everybody can make nucleic acids. Anything that's alive, right? But all of that is orchestrated by a chemistry, that is orchestrated by enzymes, that is orchestrated by protein synthesis, that is orchestrated by machinery, that is ultimately in the DNA. In other words, everything that exists today in this life, all the production of these molecules is based on the information that's already stored in the genetic information, right? So how do you make those molecules without a guide, without a plan, right? How do you make those molecules without a plan, right? So is that possible? Is there evidence to say that we could, right? And again, we have experiments that can actually show that that does happen, right? So the first one, we have something called heated clay experiment. Heated clay experiment. And this is literally what it sounds like. You get a piece of heated clay, you get a vial of amino acids, you throw on top of it, and proteins form. Alright? So it's that easy to do. You get amino acids in a vial, you throw over heated clay, and amino acids, simple peptide chains will form. To call it a protein is a little stretch. Now, these are proteins that have no function. They're just random chains of amino acids. Are you with me? So, congratulations, you achieved a protein, but you didn't make it a useful protein. Because proteins in life, each one of them is what? A shape to do a job, right? So, it's hardly a living, again, we formulate your expectation. We don't want complex proteins with a job. We just want a self-replicating molecule, right? So if one of those proteins from the heated clay has the capability of actually making itself replicate, we did it. We have the life that we did the thing that we needed. Are you with me? So and there is evidence that as far as amino acids are concerned, if a heat source is available, spontaneous formation of peptide chains does occur as long as there's heat. Right? And a surface for them to form on. And it's not hard to imagine a heated clay place on the early Earth. Right? Keep that in mind and let it simmer. See what I did there? Now, the other thing that provides evidence for this possibility is, let's talk about lipids. Okay? So for heated clay, we can see this and this. But let's talk about lipids a little bit. So can lipids form by themselves? Like, by the way, carbs, we don't need the carbs. Oh my gosh, what are you trying to say? We need energy. Yes, but we can get energy without carbs. We can get it from the sun. We can get it from a heated thermal vent. Are you with me? The carb mechanism that we have today where life uses stored energy in carbohydrates to make it, that's a complex life form requirement. We do not need that on this thing. To replicate, this thing just needs heat. Whether that heat is stored in a molecule or not is a different story. Later, we can have the use of carbs as a heat source. All we need now is heat. So carbs, but we need the lipids. Why do we need the lipids from the start? For we need a barrier, right? So what about the lipids? This is my favorite one, all right? Coacervates and spontaneous bubble formation. Spontaneous bubble. Coacervates and spontaneous bubble formation. Now, here's the thing about this thing. Anybody has ever put a bunch of oil inside of water?
Yeah.
What happens to the oil? It separates from the water. Why? It's not about density.
It's hydrophobic.
It's hydrophobic. Because you put salt in water and salt disappears in it. Surrounded, loved by the water. Right? It's like embraced, it's literally embraced by the water, like salt and sugar. It's like you're getting embraced by the water. But on the other hand, water likes some people but not others. Right? It's just like Republicans. That's what water does. It pushes them away. But you know what? The lipids push them away too. And then the result is that they cut. And now, you try it. You go home and get oil and put it on a blender with water and blend the hell out of it. And it's going to mix. And then 5 minutes later, they're separate again. Right? So this is physics. It's just the molecular interaction that exists between those two types of molecules. They do not dissolve in each other, and they push each other away. So this is actually interesting. If you have one lipid and another one over here, and they're both inside of water, what's going to happen eventually? They'll find each other and hold each other. And water will push them away. So in a way, if you really look at it, the Republicans are trying to do something nice. They're trying to bring other people together. You know? They just don't want them together with us. I'm just saying. I'm actually somewhat of a Republican too, so I'm just kidding. I'm a libertarian, so you know. So what I'm saying though is that spontaneous bubble formation is a natural process that does not need life. Are you with me what I'm saying? It does not need life. Okay? So we have a mechanism to make a peptide chain. Just all we need is heat. And all we need to make bubbles is lipids sitting in water. Are you with me? All we need now is an accident. A bubble forming around one of those molecules. And we have it right there. Are you following what I'm trying to say? So, next class I'll start from there. Now we're almost here. We just need one more step to go here. And this step is just an accident. Alright? We just need one more step. And that's just an accident. If that accident happens, now it's everything is different. So I will start with a video from next class from Think About It, which talks about how this accident happened, and then I want to continue the history. Where do we go from there? What are the milestones of early history of life on Earth, which are important for the history of life? This is origins. By the way, this is a process called abiogenesis because it does not need life to have life. Right? Now, is it true that Pasteur proved that life needs to come from other life? Well, first of all, that was 300 years ago. Get some more current information. Second of all, he did not prove that life has to come from life. He proved that complex life has to come from complex life. We're not talking about making a prokaryotic cell. We're talking about making something much similar. A protobiome, right? Something simpler than that. We'll pick it up from your next class. And it will absolutely start with an FRQ next time. Okay? So I'll see you guys then. Have a good one.
Mr. Lima, for investigation 2 for the write-up,